Alrighty, welcome back, my friends. Welcome to our next installment of this week's videos. Um, so from here, we're going to focus on waves. So we're going to jump now into chapter 8, and talk about waves of various varieties, how they form, why they form, the anatomy of waves, and things like that, which is, I think, to be kind of cool, and how they interact with the shoreline as well. So we're going to classify waves in a couple of different ways, in a sense where, how do we cause them? What are their types? Are they wind driven? Are they density driven? What size are they? Are they deep water waves? Are they shallow water waves? So what we're going to have to do here is we're going to have to kind of break our initial idea about what it is to be a shallow water wave and a deep water wave. Like when you say deep water wave, it doesn't mean that it exists only in the deep water or only in shallow water. It's going to be like how it interacts, how the wave energy interacts with the bottom of the ocean, and when does that start to occur. So there's going to be a little bit of math involved, or numbers involved, I should say. You're not going to have to do any calculations unless you're in my lab. Then yes, you will have to do a few calculations. But if you're kind of a more of a math-centered brain, then that will be of kind of the useful thing. All right. So first, we're going to talk about the causes of waves. So when we're considering how waves occur, all waves, every single friggin' one of them, starts with some sort of generating force. So some sort of cause made the energy go through water. And then the returning of that water surface to an undisturbed state is called the restoring force. And there's only two restoring forces out there. One is gravity, and the other is surface tension. So we know gravity keeps us down here on Earth, right? It's a whole thing. We're a spinning planet, so gravity keeps us solidified down to the bottom, or to the surface of our planet. Whereas surface tension, if you recall, when we talked about water, just water in general, and why surface tension is such a fascinating property of that material, that kind of will bring it back to this idea. Like when you slap your hand down onto water and it splashes everywhere, it restores back to its original position for all intents and purposes. It doesn't just like splay up. It's not like, if you've ever seen any videos of astronauts in space and playing around with water, it's not just like fluttering around, spraying everywhere. So there are several principal causes of waves. So what we're looking at here on the right side is wave period. So like how fast do they move, basically, in a way. So we have wind waves, and these are on like super small wave periods. So obviously generated by the wind. Then we have earthquakes, volcanoes, landslides, and storms can cause waves as well. Throughout the course of the semester, when I've done current weather stuff, we've seen how there's some special weather hazard statements and wave advisories and things like that. Like, okay, well, it's really crazy windy today, so probably don't go to the beach, or if you do, kind of stay away from the water line in general. And that's because there was a storm afoot, and so that has really churned up a bunch of water in terms of waves. And then we'll talk much more deeply about tides later on, and those are caused by gravitational pulls of the moon and the sun. So we also have two different kinds of waves, in a sense, where we have surface waves, which is generally created by wind motion, and then we also have internal waves. So these internal waves are created by density differences and tend to be really like large, which is really kind of fun and interesting. So with that, some examples of that would be tidal waves, turbidity currents. There's that term again. I told you that we weren't going to get rid of it when we first brought it up. That's like the that's kind of like the carving out of the submarine canyon, the Monterey Bay submarine canyon, right? So you have the sand that's kind of like churning about and then eventually settling, and we can see that as turbidite deposits. But also passing ships. If you've seen anything on social media, people going on cruises or whatever, and like you can look out at the back of the ship and you can see that the wave, or that there's some sort of mixing going on from the propellers at the bottom of the ship. Same thing for like any cargo ship or Navy ship, whatever. So this image here on the right is from a different book that I used to use, and this is a table from your book. So I just wanted to keep it in here so it looks a little bit familiar. So it just goes through the different types of waves, what causes them, what their wave period is, and various other things here. This is kind of like a little for your information, if you will. So now I want to talk a bit about the anatomy of waves. So we give names to various parts of these waves. So starting with kind of the easier ones, I suppose, we have wavelength, which is the distance between the top of one wave and the top of the very next wave. And by the way, the top of those waves, the name of that is called a crest. Perhaps you've heard of something like if you go hiking or something, the term for that is ridge. But for oceanography purposes, we're going to say that the top of the wave is a crest. Oops. Oh, no. And then the bottom of the wave is a trough. And then the wave height is determined by the top of the crest to the bottom of the trough. A couple other terms here. We have wave frequency, so the number of wave crests that pass a point at each second. And then wave period is the time that is required for the wave from crest at point A to reach point B. So if you're following a wave along, how fast it can get from point A to point B is the wave period. Whereas if you were just like a pier, like a stump in a pier, then the wave frequency would be how many waves would come by you at one part throughout a certain amount of time. In this case, each second. Then what's also really interesting is we have this term of steepness. So that's the height divided by the length. And actually when a wave breaks is mathematically determined by this value. So it's 1/7 of h over L, the height over the length. And then the wave will crash over and break as the term for it goes. What's also really fascinating, I think, about waves, in this particular case, ocean waves, is that it's not moving water, which is kind of a weird thing to think about. But there's this circular orbital motion here, and as the wave passes, it's actually the wave is energy, and the ocean is just the medium for that energy, which is really, really fascinating. So the water isn't doing the traveling, it's the energy that's traveling through the water. So in this case, we have a cute little rubber ducky, right? So behind the ducky, there's a wave crest, and the ducky is then being forced upwards in this overall circular orbital motion here. So if we were to follow the ducky around, it would make this big old circle, and the ducky would move a little bit, but not a whole lot. And it's kind of weird to think perhaps of the fact that water doesn't move with waves, because like if you go to the beach, you're like, girl, there's waves crashing on the beach. That is literally water moving, and those are literally waves. Yes, I totally understand that. But in all totality, it's really just energy that's moving through the water. Think of it this way as well. Like everything is waves, right? Sound waves, light waves. The air is a medium in which light travels through until it reaches our eyeballs. The air is also a medium of, the sound going from whatever speaker you're listening to your ears. That's a way that you can kind of think about that. Okay. So now we're going to classify waves in terms of their speed. So the wave speed varies on the type of wave that it is and how deep the water is. So a deep water wave is classified as the water depth being greater than or equal to 1/2 of the wavelength, which means that the water is deep from a wave's perspective. So energy travels down the water column, and if that energy dissipates before it starts to interact with the bottom of the ocean, then we would consider that a deep water wave. The next slide I have will help illustrate that idea a little bit better. Whereas a shallow water wave, it means that the water depth or the energy depth is less than or equal to 1/20th of the wavelength. So that means that the water is shallow from a wave's perspective. And then we have kind of like an intermediate transitional situation. So we're going in between. So transitioning from a deep water wave to a shallow water wave. This is what I mean by the energy dissipates before it reaches the bottom of the ocean. So you have this circular orbiting energy at the surface, and see how the circles are getting smaller and smaller and smaller, but there's no interaction with the bottom of the ocean. That means that it's a deep water wave. And this is just how fast the wave travels. V is just speed, which is gravity times time, I think, divided by 2 pi. So yeah, the speed is determined by the depth, or excuse me, the wavelength over the period. So the deep water wave sets these water particles into a circular motion, and again, that orbit diameter decreases with increasing depth until there is no motion at the depth of 1/2 of the wavelength. So this here, this dotted line, is called the wave base. So where that energy completely dissipates is the wave base. And then if we're looking at the speed of waves, what's really fascinating here, what we're looking at is wavelength is on the x-axis and wave speed is on the y-axis, and we're looking at different water depths. So the take-home point here is basically that there's a limit, basically, for like these for shallower water. So for 1 meter, the speed is only going to be able to be just above 2 meters per second. It can't go any faster than that. Can it go slower? Sure. But it also depends on the wavelength, right? Whereas the idea here is that if the water is deeper, the deeper the water goes, the faster the waves can travel, especially with longer wavelengths. So like, for example, just different waves can travel at different speeds. I was going to mention tsunamis, but tsunamis are not a deep water wave, actually, which can be kind of counterintuitive, perhaps. And just one last thing I want to end with for this video is the factors that can affect wave energy. So things like storms and storm centers. And, we got to kind of forget about Ekman transport for the moment. I don't want to say forget, but like we're thinking at like surface stuff. We're not thinking net transport of things. So the further away that a wave is from the center of a storm, the longer the wavelength and the period of the waves also decreases. So less energy the further you get from the storm center, from like where the most intense winds are, but it can still emanate further out from that storm. So the stronger the winds, the greater the waves. And then, sometimes we'll actually start to see wave action from storms even before a storm is really close by. Which is something that we usually see with like tropical cyclones, and when they start to get close and close to the coast of the U.S. or to the coast of wherever, they tend to be able to see the wave energy first, which is really kind of fascinating, I think. Alrighty, well, thank you so much for your time and attention. We have one more video to go for this week, and then we'll be done. So let me know if you have any questions, comments, and/or concerns. Thanks for your time and attention. Appreciate you.